Have you ever wondered how artificial intelligence can generate human-like text from simple sentence to complex stories with seemingly effortless ease? Well, this answer lies in the fascinating world of large language models which have revolutionized the way we interact with language. At the heart of these models lies a complex process that enables them to sample sentence one word at a time to create coherent and contextually relevant text. But how do they do it? In this video, we will delve into the inner workings of large language models and explore the intricacies of sentence sampling, revealing the remarkable mechanism that allows these models to generate text that is often indistinguishable from human writing. From the basics of this language modeling to the latest advancements in artificial intelligence, we will break down the magic of large language models and uncover the secrets behind their sentence sampling proneness. So let's get started with understanding an overview of large language models. So basically, this large language models like transformers, they sample a sentence by predicting the next word in a sequence one word at a time based on the context of previous words. And this process is called decoding or generation. And here is a simplified overview of how it works. So first of all, the model will start with a prompt, which can be a single word, a phrase or an empty sentence. After this, the model will process the prompt and generates a contextualized representation of input, which captures the meaning and relationship between the words. Then, model predicts the next word in a sequence by computing a probability distribution over the entire vocabulary. And this distribution is based on the contextualized representation and the model's understanding of language patterns, grammar, and semantics. Then model samples a word from the predicted probability distribution, and this can be done using various sampling strategies. After this, it repeats the steps of prediction and sampling with the newly sampled word added to the sequence until a stopping criteria is met. Now, the stopping criteria can be the sequence reaches a predetermined length, or a special token is sampled indicating the end of sentence. And finally, this generated sentence may undergo additional processing such as spell checking, grammar correction, or fluency evaluation. Next comes the decoding strategies, where first is greedy decoding, which is the simplest decoding strategy, where the model selects the word with the highest probability at each step. So while efficient, greedy decoding can lead to suboptimal results as the model may not consider the overall sequence context. Next comes beam search, which is a heuristic search algorithm that maintains the set of candidate sequence, that is the beam, and iteratively expand them to find the most likely sequence. Here the beam size is a hyperparameter that controls the trade-off between computational cost and search quality. Next comes top K sampling, which is a variant of beam search that samples from the top K most likely words at each step. And this approach can be more efficient than beam search because it reduces the number of candidate sequences to consider. In nucleus sampling, we sample from the top P percentage most likely words, where P is a hyperparameter. And this approach can help to reduce the impact of outliers and improve the overall quality of the generated text. And finally, this diverse beam search is a method that encourages diversity in the generated sequence by using a diversity promoting objective function. And this approach can help to generate more varied and interesting text. Next comes the sampling techniques. Well, first of all, it's a temperature sampling, where it controls the randomness of the sampling process. Higher temperature leads to more random sampling, while a lower temperature leads to more deterministic sampling. Next comes top P sampling, which is a technique that samples from the top P percentage most likely words, where P is a hyperparameter. And this approach can help to reduce the impact of outliers and improve the overall quality of generated text. Annealing is a technique that gradually decreases the temperature during the sampling process. And this approach can help to improve the quality of generated text by allowing the model to explore a wide range of possibilities. Now, for evaluating the efficiency of large language models, we use these evaluation metrics, where perplexity is a measure of how well a language model predicts the test set. A lower perplexity indicates better performance. Blue score is a measure of similarity between the generated text and the reference text. Higher blue score indicates better performance. Next, the roughest score is a measure of similarity between the generated text and a reference text. Higher roughest score indicates better performance. Now, Meteor score is a measure of similarity between the generated text and the reference text. Higher Meteor score indicates better performance. Now, there are certain challenges involved in the process. First, mode collapse, which occurs when the model generates limited variations of the same output. And this can be addressed by using techniques such as diverse beam search or nucleus sampling. Overfitting occurs when the model is too complex and fits the training data too closely. So this can be addressed by using techniques such as regularization or early stopping. Underfitting occurs when model is too simple and fails to capture the underlying patterns in the data. And this can be addressed by using techniques such as increasing the model size or using more advanced architectures. Now, its future directions includes multimodal generation, which involves generating text, images, or other forms of media. And this can be achieved by using multimodal models that can process and generate multiple forms of input. Explainability involves understanding how language models make prediction and generate text. So this can be achieved by using techniques such as attention visualization or feature importance. Now, adversarial robustness involves making language models more resistant to adversarial attacks, and this can be achieved by using techniques such as adversarial training or input validation. Next comes advantages and limitations. So this LLM's ability to sample a sentence using probability distribution has several advantages, like LLMs can generate a wide range of possible sentences, allowing for creative and diverse output. Also, LLMs can take into account the context of input sentence and generate output that are relevant and coherent. But there are certain limitations, like the random number generator introduce an element of randomness into the output, which can make it difficult to control the exact output of large language models. Also, large language models may reflect biasness present in the training data, which can result in output that are not representative of desired distribution. Now, how does LLM sample a sentence? So here we will walk through this process. So first of all, we have an input embeddings, where large language model starts with a sequence of input embeddings represented as this first column. So these vectors are the numerical representations of input words or characters. Then feeding input embeddings. So here this input embeddings are fed into the large language models, which process them to generate the next output word. Then predicting probability distribution. So here large language model predicts the probability distribution of the next output word over a vocabulary of 10 words. And this is represented as a column vector. And here the probabilities are calculated and then written below. So with the cumulative distribution calculated by hand. So this cumulative distribution starts with 0 at the bottom and adds up to the 100 at the top, ensuring that probabilities add up to 100%. Then we will draw a random number. So a random number, say 0.64 or 0.65. Here we will take 0.65 and it is drawn. And the range is in the cumulative distribution of 0.45 to 0.95. So here the number is lying. So how and why? This can be there. Then we will select the next word. So this corresponding word how is looked up and filled in the first blank. Then we will repeat this process and we will get the next word as R, because it is the 0.92, which will lie between the 0.5 and 7 and the 97. Then we are having a third word 0.52, which will lie after 0.47. So we are getting the three words as how are you. So here we are selecting these words like this, and finally we will see some key concepts here. And the key concepts involved in this are randomness, that says that large language models outputs are generated using a random number generator, which introduces randomness into the process. And this randomness is like throwing a dart at the dartboard, where the outcome is unpredictable, but the probability of landing in certain areas can be estimated. Then the diversity, which says that randomness in the large language model outputs give rise to diversity in the generated text. This means that model can produce different outputs for the same input, making it more creative and flexible. Temperature is a hyperparameter that controls the degree of diversity in the large language model's output. Higher temperature can lead to more diverse outputs, while a lower temperature can result in more predictable outputs. So here temperature is not used in the exercise we just discussed, but it will be explored in more advanced exercises. Then comes inverse transform sampling. So this process of generating text using the large language models can be seen as a simplified version of inverse transform sampling, which is a technique used in probability theory to generate random samples from the probability distribution. So in this case, the large language model predicts the probability distribution of the next output word, and the random number is used to select the corresponding word based on the cumulative distribution. Next comes probability distribution, which is predicted by the large language models, and it represents the likelihood of each word in the vocabulary being the next output word. This distribution is typically represented as a vector of probabilities where each element corresponds to the word in a vocabulary. Then this cumulative distribution is calculated by summing up the probability of each word in the vocabulary, starting from the bottom of the distribution. And this creates a monotonically increasing function that represents the cumulative probability of each word being the next output word. Then random number generation, which is used in large language models. It's typically a pseudo-random number generator which generates a sequence of numbers that appear to be random and uniformly distributed. Next comes the second example. So to illustrate how large language models sample a sentence, let us consider an example. Suppose you want to generate a sentence using the vocabulary of 10 words. The cat sat on the mat and ate a treat. Here the large language model will predict the probability distribution of the next output word, which might look like this, which is shown in the left here. Then its cumulative distribution is shown on the right part. So if we draw a random number between 0 and 1, say we are taking 0.62. So we will select the word the as the next output word, because this 0.62 will lie between the 0.50 and 0.65. Okay, and that's the wrap. The large language model's ability to sample a sentence using a probability distribution is a powerful tool for generating creative and diverse text. However, it requires careful consideration of the advantages and limitations of this approach to ensure that the outputs are relevant, coherent, and free from bias. So as we unlock the full potential of these models, we may soon find ourselves wondering not how large language models sample sentence, but how we ever manage without them, and what incredible possibilities the future of large language model generations holds. So thank you.